Hello everyone, my name is Xiaohao and I'm from Fudan University. Today I will present our work how Android developers handle evolution-induced API compatibility issues, a large-scale study. This is a joint work with researchers from Purdue University. It is well known that Android is evolving rapidly. During Android's evolution, new APIs are introduced and some old APIs are removed. We can see this from the figure on the right. Large version updates will introduce more than 3,000 APIs, or delete more than 1,000 APIs. And when app call these unsupported APIs, it will crash with no such method error. For example, the figure below is in runtime log for this issue. After investigation, we find Compatibility Check is a standard way to handle these issues, and we divide these checks into two types, SigChk and Replacement Check. Look at the figure A. SigChk just check the underlying API level. Here is the check SDK int greater than or equal to 22. SigChk is easy to adopt, but may cause inconsistent bugs or experience, as the app do nothing when SDK int less than 22. The figure B is Replacement Check. It provides the similar functionality on unsupported API levels. So we think Replacement Check is a better way to deal with compatibility issues. However, there are several challenges in differing Replacement Check from SigChk. First is that control structure does not reliably distinguish Replacement Check from SigChk. Some people may think the code with single if structure is SigChk and the code with if and else structure is Replacement Check. Actually, this is not true. We can see the figure A. It has if and else structure, but it is a SigChk, because it just print a log on unsupported API level. And the figure B is the real Replacement Check. The second challenge is that similarity between the true and false branches does not accurately differ these two checks. In the below code, two branches are very similar, but the false branch lack the important function make custom animation. Despite many challenges, we design an excellent tool, Rp, to detect and classify compatibility checks. Rp has two main components. One is static analysis component. The other is feature extraction component. In static analysis, this tool first identifies compatibility checks by taint analysis. Then, it extracts related code blocks for the check. These code blocks will be sent into features extraction component. In features extraction, Rp will compare unsupported API with every API in the other branch. By doing data flow analysis, Rp can extract both behavior semantics features and input-output dependencies features. These features will be converted into feature vectors for classification. I will briefly introduce the two feature sets we selected. The first feature set is called the Behavior Semantics feature set. This set has 8 features. They are based on the class name, method name, modifier and comments of the two compared APIs. Class and package name similarity are splitting name into word set and calculating the similarity. Common package prefix length and package hierarchy distance are the similarity between packages. API name is like a natural sentence. It contains nouns and verbs. Operation action and target similarity are the similarity of verbs and nouns. The last is comment similarity. We transform the comments into word set and calculate the similarity. The second feature set is input-output dependencies feature set. This set has 11 features. They are mainly about the similarity of arguments and return value. See the figure below. Input variable set and output variable set are based on data flow analysis. Input is a set of blue variables and output is the green variables. Operation set is similar to variable set. It contains the system API invokes and data flow path. Before starting the large-scale research, we first evaluate the effectiveness of our tool. First, we manually analyze 293 checks to build our training set, which cover 123 different APIs. And then we randomly choose 414 checks for validation. These checks have no overlap with training set. As we can see, our tool achieves a quite good performance on both data set. Besides, we also evaluate the contribution of two different feature set. We find it is necessary to including both feature set. After proving the effectiveness of our tool, we conducted a large-scale application analysis. Our research has 3 main research questions. We crawled apps from Google Play and third-party app markets, including their top-ranked apps. As shown in table, we collect 309,967 unique apps. We run Rapid in parallel to analyze these apps and set the timeout for each app to 5 minutes. In all, Rapid successfully analyzed 296,133 apps with 12,470 apps timeout. Only 1,364 apps failed to parse by FlowDroid. In research question 1, we have 3 main findings. Finding 1 is 83.41% apps are affected by this issue. This result shows that compatibility issues are indeed prevalent in Android apps. Finding 2 is the ratio of replacement check is quite low, which calls for improvement. Finding 3 is control flow structure is not reliable in differing single check and replacement check. Our tool is necessary for replacement check classification. In research question 2, we have 3 main findings. As shown in the figure, Google gives recommendations for some deprecated APIs in the comments. However, only 130 of 2,850 compatibility-related APIs of Google recommendations, while they greatly help developers better handling compatibility issues. As shown in the table, the replacement check ratio of APIs with recommendations is significantly higher than those no recommendations. At last, some Google's recommendations are not followed. For those incompatible API invocations that are not replaced in the recommended way by Google, we further investigate the underlying causes. Overall, we observe 2 main reasons that cause developers to handle compatibility issues in a different way. The reason is the recommended API needs extra parameters. For example, in line 1 of the second table, Google recommended API need a new parameter theme. The reason B is a quick replacement exits. For example, in line 2 and 3 of the second table, static fields can be used to replace incompatible API. In research question 3, we have 2 main findings. We find 1,086 of 2,850 compatibility-related APIs have replaced implementation in our data set, while Google has recommendations for only 130 of them. By using the seen replaced implementations, the ratio of replacement check can increase from 38.4% to 83.3%. This gap shows that there is a great room to improve the current practice of handling compatibility issues. In general, our work find and differ 2 kinds of compatibility checks, and we design an automated tool to differ single check from replacement check based on static analysis and machine learning. At last, we perform a large-scale study on compatibility checks. We find fixing evolution-induced API compatibility issues is still a challenge, so it is important to provide easily adoptable recommendations. And we think mining the fixed solutions from experienced developers can significantly help novice developers. Thank you.